Recording on. Probability. Okay, so this is our second session on probability. And what we're going to do today is going to revisit the binomial expansion via Pascal's triangle that we covered last week. Look at the binomial series, which is a formula method of determining the binomial expansion. And look at how the binomial distribution can be used, both in a basic way and in industrial inspection. Okay, so kind of try and tidy up a little bit what we started to cover last week, and then carry that on into some practical uses of that expansion. So we looked at this last week, binomial series. Binomial expression is one which contains two terms connected by a plus or a minus sign. Examples include p plus q, a plus x all squared, 2x plus y all to the power of 3. If we expand those expressions for integer values of n, so a plus x to the n is a general way of writing those. If we expand them for n from 0 to 6, we get the results shown at the bottom. Okay, so you can remember covering that last week, and I'll just go through the expansion of a plus x all to the power of 3 again. I've got a typed out solution. So if we look at the top line, a plus x all to the power of 3 is the same as saying we're going to multiply 3a plus x in brackets terms together. If we then look at expanding the first pair of brackets in that expression, that's these two, we get a times a is a squared, a times x is ax, the other a times x is ax, and lastly x times x is x squared. Yeah, so that we can then simplify that term into that red term, so bring the two terms in the middle that are like terms together as 2ax. So that expression there, highlighted and in red, is a plus x all squared. There. We know to get a plus x to the power of 3, we now multiply that bracketed term by a plus x. So multiplying out those two sets of brackets, we get a cubed. So that's a squared times a is a cubed. A squared times x is a squared x. 2ax times a is 2a squared x. 2ax times x is 2ax squared, and so on. Carry on with that. And then the yellow and the green like terms can be brought together into a final expression, and the bottom here of a plus x all to the power of 3 is a cubed plus 3a squared x plus 3a x squared plus x cubed. All right, and that table, or that final, this table down the bottom here, is that done up to a plus x all to the power of 6. Okay, now there's some observations we can make of that triangle table in terms of, if we look at the powers of a, the a there, so let's take this a to the 4 one. The power of a is 4, then it goes to 3, then it goes to 2, then it goes to 1, and then it disappears. So the power of a decreases from left to right at each term. If we take the a plus x to the 5 one and look at the powers of x, in the first term there are no powers of x. Then there's x to the 1, x to the 2, x to the 3, x to the 4, x to the 5. So the powers of the x in the a plus x increase as we go from left to right. Then, if we look at, we put a line of symmetry down the middle here, and look at the coefficients, the numbers in front of the expressions. I'll go blue. We've got, they're symmetrical about that center line. So we've got 3 either side of that center line. Here we've got 10 and 5 either side of the center line. Here we've got 20 in the middle. We've got 15 and 15, 6 and 6, symmetrical either side of that center line. Okay. Lastly, the coefficients in that table, separated out, form Pascal's triangle, where the number, any number in there, is equal to 2 numbers above it added together. So that 4 comes from the 1 and 3 above. This 15 comes from the 10 and the 5 above. So you can always build the next line of a Pascal triangle by adding the pairs of numbers together. We always know that 1 goes on both the 2 outsides. So outside is always 1, 1 and 1. And then in here it goes 7, 6 and 1 added together. This would be 7. This would be 21. That's 21. That's 35. And in there is 35. So that would make a plus x to the power of 7. All happy and clear about that in terms of Pascal's triangle. Yeah. And you could use that up to values of n of about 10. Beyond that, probably get a little bit unwieldy and just quickly fill your paper up with terms, then you might get lost. Okay. Yeah. Everyone happy so far? So if we use that to try and build the full expression for a plus x to the 7, so I've done this new line for a plus x to the 7 on the previous page. This one here, by adding the terms together above. And so we can build the expression. We know it starts with a to the power of n. Yeah. Then we bring down the, so that's comes from the 1. The second is 7. Take 1 off the index of a to make it a to the 6 and x to the 1. 21, second one. 21, a to the 5, x to the 2. 35 comes from there. 35 comes from there. 21 from there. 7 from there. And the last one is 1. So that's how we can build a binomial expansion from the Pascal's triangle, because we know that the Pascal's triangle gives us the coefficients underlined in red. We know we start off with a to the power of 7, and the index of a decreases as we go from left to right. And we know that the power of x increases as we go from left to right. So we end up with x to the O first, then x to the 1, then x to the 2, and so on. Are you all happy with that explanation of how to use Pascal's triangle to develop an expression?
Yeah, just a quick question. So if you had a plus x to the 8, the next row,
Yeah.
What would be the middle number? It'd be like 70 a something x. What would be the a and the x on that?
Well, you'd have to build the whole thing, wouldn't you? Because you'd start off with a to the 8. Yeah.
Yeah.
Then you'd have that would be, you'd be joining 7 and 1 together, plus 8.
Yeah.
A to the 7.
Yeah.
X. Yeah. Plus.
Yeah. Plus
28.
7, yeah. 28.
A to the 6 plus x squared. Yeah, and so on. Yeah.
Okay. Would it be x squared or would it be x cubed?
What, the next term?
No, the 28. No, the 28a to the 6 plus x squared. Would it be x squared or x cubed?
That's x squared.
Okay.
Because we have to remember the power of x is 0 on the first term. Oh, hang on, sorry. Yeah, 0, 1 on this term, 2 on that term, 3 on the next term, and so on. And you'll end up on the right hand end. You should end up with x to the 8 as well.
Yeah. Got you.
Yep. Okay.
Okay, so it always works.
So draw, if we want to do, without looking back, using Pascal's triangle, the expansion of a plus x to the 4, we know we can build our Pascal's triangle quite easily, because it starts with 1 at the top, and then we know it's always got 1 on the ends. So that top one is a plus x to the 0. This is to the 1. We know we're going to have a 2 in the middle there and 2 1s either side. That's a plus x to the 2. 1 outside, 3, 3, 1. That's a plus x to the 3. So a plus x to the 4 has got a 1 there, a 4 there, a 6 there, a 4 there, and a 1 there. So this line here is a plus x to the power of 4. Yeah, everybody follow that?
Yeah.
So now I can build my expression, because I know that I've got to start with a to the 4. Then I've got to add 4 a to the 3, take 1 off the index of a, x, plus 6 a to the 2, x to the 2, plus 4 a x cubed plus x to the 4. So that's how you build Pascal's triangle, or from Pascal's triangle, the binomial expansion. So the 2 1s go there, the 2 4s there and there, and the 6 comes from there. All fairly happy with that?
Yeah. So I was just doing the next one just to see if I could do that on my own.
Okay. So everybody understand that, yeah? So what we're going to look at now is the formula method of binomial expansion. So this can be used to expand any term, and you can pick out single terms if you know how the formula works. So let's just get this other computer on it. Binomial series is a formula for raising a binomial expression to any power without lengthy multiplication. The general expansion of a plus x to the n is given by that formula. The items in red highlight where the coefficients come from. The coefficients are the numbers that you get from the Pascal's triangle. So there's a coefficient of 1 on the first term. The coefficient of the second term is always n, and then the coefficient of the third term is n brackets n minus 1 over 2 factorial. Second term, I'll explain factorial in a minute. Second term is top of the fraction is n brackets n minus 1 brackets n minus 2 over 3 factorial. Does anybody know or remember what the 2 factorial, 3 factorial, 4 factorial means?
Could you just go back quickly just so that I could write down that
yeah, I'm going to go back in a minute anyway, yeah.
No worries, I'll wait it out then.
So 2 factorial, 3 factorial, 4 factorial. They're a quick way of writing 1 times 2 is equal to 2. 1 times 2 times 3, 6. 1 times 2 times 3 times 4 equals 24. So factorial means multiply all the numbers up to that number together. Yeah. And you have a button on your calculator that will do factorials. You should do if you got your scientific calculator with you. All right. So let's have a look and see if we can see how we can use that binomial series to build the same a plus x to the 4 expression. And we can check that with Pascal's triangle. So looking at what we've got here, the coefficient of the first term is 1. The coefficient of the second term is n. And then here in the third term, we've put n brackets n minus 1 over 2 factorial. We've got in the third term, sorry, the fourth term, 4 minus 1, 4 minus 2 over 3 factorial. And then lastly, 4 times 4 minus 1, 4 minus 2, 4 minus 3 over 4 factorial. Yeah. We can simplify those out. So this is 4 times 3, 1 times 2 on the bottom, 4 times 3 times 2 over 1 times 2 times 3, 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. Now that last one all cancels out to become the 1 in there. You put these numbers in your calculator. So on the top, you've got 3 times 4 is 12, times 2 is 24 on the top, and 1 times 2 times 3 is 6 on the bottom. So you have that 4 that's in there. This one, 3 4s are 12, divided by 2, gives us that 6 in there. This one's straight the value of n, and this one is 1 that comes from here. So yes, the formula could get unwieldy like anything else, but if you know that you want this fourth term here or this third term, you can just use the one part of the formula for the 1, 2, 3, fourth term, or the third term, to find what the coefficient is if you're not interested in the others. So it can be a quick way to get to one or more terms in the expansion. All right, and again, the result there checks off against Pascal's triangle entry for a plus x to the 4, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Okay. So, haven't done that. Everybody happy? Someone wanted me to go back to something earlier.
Yeah, just quickly the equation, just so that I can finish writing it down.
This one? That one?
That one, yeah, exactly.
So having said that, we can then say that binomial distribution can be used for finding, say, the probability of getting 3 heads in 7 tosses of a coin, or an industry for determining the defect rates as a result of sampling. So one way of defining a binomial distribution is as follows. If P is the probability of an event happening, and Q is the probability it will not happen, then the probabilities of the event happening none, 1, 2, 3, up to n times in n trials are given by the value of the successive terms of the expansion Q plus P to the n, taken from left to right. Hence, that's why we've learned how to expand Q plus P to the n. We learned it with A plus X, but that's besides the point. Note that the probability of the event not happening, Q, is first in the expansion, and the probability of it happening, the P, is second in the Q plus P term. All right. So here, if we were talking about a toss of a coin, okay, and P was the probability that you get heads, Q to the n is no heads. Q to the n minus n, Q to the n minus 1 is 1 head. That's the probability of getting 2 heads, 3 heads in n tosses of the coin. Yeah. So we'll have a look at an example that might better help to show how that works. So we'll look at this problem. Determine the probabilities of having A, at least 1 girl, and B, at least 1 girl and 1 boy in a family of 4 children, assuming equal probability of male and female birth. So if we say P equals probability of a girl, Q equals probability of not girl or a boy. Yeah. What does P equal in this problem in numbers?
Does P equal?
Well, it's got to be equal probability of male and female. And the 2 probabilities, P and Q, have got to add up to 1. So the probability of each of them must be
0.5.
Yeah. And what's n in this question?
4.
4, yeah, because there's 4 children. Yeah. So what we need are, from the Pascal's triangle, the coefficients for P, sorry, Q. I'm getting it wrong myself now. We need to expand Q plus P to the 4. So someone who's can get Pascal's triangle in front of them. What are they? Oh, I've got it on here. So if we look at Pascal's triangle,
1, 4, 6, 4, 1.
4, 1. Yeah. So we know what we got to do. We got to start with Q to the 4. Yeah. Then we've got to add N. So we've got to add 4 Q to the 3 P. We've got to add 6 Q to the 2 P squared. We've got to add 4 Q P cubed. And we've got to add P to the 4. Remember, Q is the probability that there aren't any girls. Q is the probability of the child not being a girl. So, on that basis, this one is Q times Q times Q times Q. It's a probability of there being 0 girls. This is 1 girl. This is 2 girls. This is 3 girls. And this is 4 girls. Because what we're saying is, remember, if we have the word and between probabilities, for 4 girls, we're saying child 1 is a girl, and child 2 is a girl, and child 3 is a girl, and child 4 is a girl. So we would multiply all those probabilities together, i.e. we'd put it to the power of 4. Yeah. Take the middle one, 2 girls, that means 2 are girls and 2 are boys. So we've got the probability of girls squared and the probability of boys squared. Now, what do we need to do if Q to the 4 is a probability of 0 girls, Q to the 3, 4 times Q to the 3 times P is 1 girl? How do we find probability of, the total probability of at least 1 girl?
Put the P and Q into the equation, do you not?
Yeah.
Up to 1 girl. So Q4 plus 4Q3P, but this whack the 0.5 then.
Well, this one's got 1 girl, hasn't it? So is this. So is this. And so is that. Yeah. The only one that hasn't got a girl is the Q to the 4 on the end, which is 0 girls. So what we can do is say probability of at least 1 girl equals 4 Q to the 3 P plus 6 Q squared P squared plus 4 Q P cubed plus P to the 4. So if we add all them together, we've got all the probabilities that have got at least 1 girl in them. And so we can expand that out. 4 times Q 0.5 to the 3 times 0.5. That's that first term. Plus 6 0.5 squared. 0.5 squared. That's this term. Plus 4 times 0.5 times 0.5 cubed plus 0.5 to the 4. So you add all those terms up in your calculator, and what you should get is 0.9375. Now, can anyone think or see of a way that you could do that slightly differently and perhaps a little bit easier? From the facts that we learned about probabilities last week and has also been mentioned this week.
Could you do like 4/5 perhaps?
Do what?
4/5, because there's like 5 chances on there and only 4 of them give you girls. I don't know, I'm spitballing. Actually no, that wouldn't work. No.
What must always be the case with a set of probabilities?
It must equal 1.
They must all add up to 1. So if we take, we know that every one of these terms, that one, and that one, all of them,
just do
added
q
together
to the 4 and then take
equals
that
1.
off 1.
So we could also say this equals alternative method is that it equals not a very good color. Alternative is 1 the whole minus this first term for no girls, q to the 4 equals 1 minus 0.5 to the power 4. Yeah, and you should get the same answer, 0.9375. It's also worth remembering that 1 is a check of the other. Yeah. Hopefully, if you do 1 minus 0.5 to the 4, you get that answer. Yeah, 0.9375. Okay. Now, B is at least 1 girl and 1 boy. So which terms do we want here for at least 1 girl and 1 boy?
The 4
1, 2, and 3.
Yeah, the 3 middle ones.
The 3 middle ones, yeah. If we mark them off, we don't want that one because it's got no girls. We don't want that one because it's got no boys. But we want that one, and that one because they've got at least 1 girl and 1 boy. Yeah. So B, prob of at least 1 boy and 1 girl equals 4 q to the 3 p, yeah, 4 q to the 3 p plus 6 q to the 2 p squared plus 4 q p to the 3. That's 4 times 0.5 cubed times 0.5 plus 6 0.5 squared plus 0.5 squared plus 4 0.5 times 0.5 all cubed. Yeah. And then you do that, you should get 0.8750. Equally, you could do 1 minus the outside 2.
Yeah.
Yep. Are you all okay with that? Is anybody lost? Please shout if you're lost. Right, I'll move on then. We're going to look now how that can be used in a more industrial inspection kind of situation. So binomial distribution used in industrial inspection. And your question on this topic in the assignment is one similar to this. In industrial inspection, P is often used as the probability that a component is defective, with Q being the probability that a component is not defective or is satisfactory, whichever way you want to look at it. Yeah. In this case, binomial distribution defined as the probability the event will happen 0, 1, 2, 3 to n components drawn at random from a large batch of components as given by the value of the successive terms in the expansion Q plus P to the n from left to right. Yeah. So when we expand it, starts off the terms with none faulty, 1 faulty, 2 faulty, 3 faulty, 4 faulty from left to right in the expansion. So we'll have a look at an example question around that, work on it together, and then I've got a couple for you to have a go at. Okay, so a machine producing a large number of bolts automatically. In a box of these bolts, 95% are within the allowable tolerance values with respect to diameter. So the remainder are outside the diameter tolerance value. 7 bolts are drawn from random from the box. Okay, we're going to determine the probability that 2 are faulty and the probability that more than 2 are faulty. So first of all, what is P, which is the probability that the event, that the item chosen, an item chosen is good. Hope I got that the right way round. P is used, the probability is defective, sorry, P is defective. So in this case, what does P equal?
5%.
5%. In decimal terms, 5% is?
0.05.
Yeah. Therefore, if they're going to put that up to 1, Q must be 0.95. Yeah. And what's N in this case?
7.
7, yeah. Because we're going to draw 7 sample bolts from the box. Yeah. So we need to find the probabilities of 2, we need to expand Q plus P to the 7. So we need the 7th line on the Pascal's triangle. Seventh line. I've got 1, 7, 21, 35, 35, 21, 7, and 1. Does everyone agree with that? We expanded that earlier.
Yeah.
Yeah. So it's going to be Q plus 7. That's going to be Q to the 7, sorry, plus Q to the 6 P plus 21 Q to the 5 P squared plus 35 Q to the 4 P to the 3 plus 35 Q to the 3 P to the 4 plus 21 Q to the 2 P to the 5 plus 7 Q P to the 6 plus P to the 7. All agree with that? And in terms of what each term in there means, the first one is none faulty, the second one is 1 faulty. Two faulty, 3 faulty, 4 faulty, 5 faulty, 6 faulty, 7 are all faulty. Yeah, do you all understand that? So, which terms do we need for 2 faulty?
Just the one, isn't it? Just
Just
21
the one
Q4,
term.
Q2.
21 Q to the 5 P squared. 21 times 0.95 to the 5 times 0.05 squared.
Zero point zero 0.041.
0.0406 I got here, yeah, so you're right, yeah. Yeah. Okay, so that's the probability of 2 faulty. What terms do we need for more than 2? How do we calculate more than 2?
Would you cross off the first?
The first
3. So would you cross off 0, 1, and 2 and work from
Yeah,
3 onwards?
Yeah, and add the rest together. So you can either do at least 2 is equal to this term, this term, this term, and this term all add together. Yeah. So that would be 35 q to the 4. So that's 0.95 to the 4 plus 35 times 0.95 to the 5 plus 0.05 to the 4 plus 21 p 0.05 to the 5. So this is 3 plus 7 0.95 times 0.05 to the 6 plus 0.05 to the 7. Alternatively, you could do 1 minus the first 3 added together.
That's what I'm doing now.
Or 1 minus q to the 7 plus 7 q to the 6 p plus 21 q to the 5 p squared. Either way, the result you get should be 0.0038. Okay.
Yeah, just give me a sec longer. I just want to check that I've got it written down right.
What you're really interested in here is what sample size is going to give you the best chance to find out if there's faulty product in that box.